Good morning. Welcome to this live session in Mathematical Methods in Engineering Science by NPTEL. We have arranged this live session at the end of module 1 to discuss any query, any doubt that the students would have, and they can come here live in this hangout session. With me, I am Arindam, and with me this is Ankur, and in the queries Mahendra and Sunish, we are assisting, we are being assisted by them. So, feel free to send anything that you feel like asking in module 1, which were mostly based on linear algebra, and in between, I mean, when we get questions we will try to answer. In between we will talk about the assignments and assignment problem solutions. We will show the basic concepts and the solutions that we need to discuss. We will discuss a lot of them, perhaps not all of them, but a lot of them. And a note on assignments: some people in forum, they have complained that the assignment is subjective and perhaps it takes more time. True, but believe me, at our end also it takes more time to evaluate them, subjective evaluation, but still we take the pain, because we believe, the team believes, sir believes that way people will learn more. So, we will have these discussions as we will go along. So, we will start with assignment 1. Assignment 1 first. It was basically first two problems. If we look at it, we can do the outline of this. So, first problem was, matrix was given like this. This matrix, this equals this. So, we need to find this type of decompositions, which is mostly known as LL transpose. Notice that here basically it is called Cholesky decomposition, which we will find out. Basically in this case, if you look at this matrix, this is symmetric matrix. So, that is why we will soon see another problem where if it is not symmetric, how this is slightly different. So, for this basically we can straight away write, you see, matrix multiplication is basically multiplication of rows into columns. So, basically you can straight away write from this a square equal to 4, and in the problem it was said that only take positive square roots, and you should when you do Cholesky decomposition. So, from that you will get a equal to 2, and like that, I mean, if we can do that continuously, like here you will get AB, that is also equal to 2, implies that B equal to 1. So, like that you will get all the values. It is not really that difficult, you can understand if you look at it, but the real problem will come if you go on doing it. Once you come to the last point, that is, we need to find the value of f. Here f will turn out to be a complex number, okay, minus 1, okay, that will be a complex number. So, which will basically show that this matrix is not, I should say that, is not positive definite. So, if it is a complex number, anywhere it cannot, because in Cholesky decomposition we are expecting real numbers. It is not. So, because that because of that it is not positive definite. So, that is how you should find it, and you should find it at the end. That will comprise of the complete solution of the problem. Okay. So, okay, the next problem talks about a linear transformation, that is 2, 3, okay, and 4, 5. Okay. So, So let's call this linear transformation A, which does to vectors 2, 0, 1 and 1, 6, 0. Okay. So this to this, this to this. So first of all, we are required to find the domain and codomain of transformation. So that is, I think, quite clear. We don't need to talk about it. That is in R2, in R3. So that gives you the dimension of the matrix. So talking about the range and the null space, somebody talked about column space also. So in that you can find the range space and null space here, but more than that, that is not that important, because we need to first find the matrix A here, I think. So for that, we will not find the whole matrix here, we will just show how to do it. So we can write this as, you know, A1, A2. So X1, X2. Basically, what you want to write is Ax equals to y. So this is a matrix, this is a vector, and in that we denote the columns as A1, A2, and we have this X1, X2, Y1, Y2. So these A1, A2 are columns. So from this you can actually solve it, because it is all given, it is not that difficult, and the answer is minus 7 by 2, 9, 5 by 2, 3 minus 6, 2. That is the answer. So that should not be a problem, I think. It is a very straightforward problem. So coming to problem number 3, there is not much to calculate here really. It talks about a linear transformation A and distinct vectors x0 and x1. Notice the word distinct here, that word distinct is important, and we will soon find out why. Are found to be pre-images of a given vector y0. Yes. So by some sort of a linear transformation, both of them get mapped to y0. So what can be said about the null space of A? So null space of A, let us denote this by NA. Can we say something? It is more of a qualitative notion than quantitative, but what can we say about null space of A? Now if this linear transformation A maps x0 to y0 and x1 to y0, then we can say x0 equal to y0 and x1 equal to y0. Both of these statements are valid. Okay. So now if you subtract 1 from 2, so 2 minus 1, sorry, so will give me, so a1 of x1 minus 0. So now comes the point of being distinct. Here is the point of being distinct. If they were not distinct, then this was 0, and that we consider, do not consider for null space, because that is a trivial solution. So, here we can say because x 1 and x 0 are distinct, that is something, let us say something like this we denote x d, then we can say implies x d equal to 0, and there is something non-zero in the null space. Okay? Something non-zero is in the null space, that is x d, and we can say if we have to describe the whole of null space of A, all of null space of A. So, basically this is not N A, this is the, no, we can say basis of N A. So, basically we will say N A is equivalent to, we will say some alpha x d, alpha scalar. So, alpha is a scalar, alpha x d, this describes the whole of null space of A, this whatever this transformation is, linear transformation. So, I think that settles for question 3. Question 4 basically is about Gram-Schmidt orthogonalization. We will not talk about it in detail here, because that is a long process, it is a very well known algorithm, but I will just give you the answers. I will just give you the answers that I have got, and I believe that is correct. So, I think the vectors was okay. U1, this is problem number 4, assignment 1. So, 2 0 minus 1 1 transpose U2 1 to 0 3, always transpose, save space, 3 0 minus 1 2. So, these are the three vectors that have been given, and we are asked to do Gram-Schmidt basically. Given any number of vectors, if there are, suppose given a set of n vectors, and you are asked to do a Gram-Schmidt, that means basically you are talking about in a space of, Rn, you are talking about finding the orthonormal basis of that space Rn, and if the n set of n vectors, those n vectors, some of them turn out to be linearly dependent on some others, then in the orthogonalization process we will find out, and we will only get that many orthonormal basis which is equal to the number of linearly independent vectors in this set. So, basically first is unit vector along U1, which you get basically this is basically a vector by the norm of that vector. So, you get 0.82. I hope you got it, because it is not that difficult at all, because all the process has been detailed in the question how to find that. So, you should be able to find that, just have to follow the steps. This is U1, okay. Then for the second one you find V2, let me denote it by this, and I am giving you the straight away the vector after normalization, and that is minus 0.21, okay, 0.64. Be careful while calculating these things, because they are sometimes messy. Into 7, 0.69. Okay. So, for V3 we find 0.10 minus negative 0.31, 0.37, 0.17. So, I gave you the answer directly here without explaining because you know Gram-Schmidt. If you do not know, then just quickly look up a book or some linear algebra book or some online lecture, and also you can quickly follow the MMEF's courses lecture. Then you will find it is just basically a logical algorithm more than anything, and all the process has been described, how to subtract the component, and then you, after subtracting the component of the projection, you just do this thing, that where you normalize the vectors to find it orthonormal basis, not only orthogonal, orthonormal, that means not only they are orthogonal, they also add up to the 1, the column vectors. So, okay. Question 5, that is a long one, I will not, I just had the diagram here in the beginning to save some time. So, it basically talks about changing the unit of measurement from one system to another system, where the surveyor has the data in the local system and he wants to convert it. So, he needs to do proper linear transformation. So, we are asking for the linear transformation here, and if you can look at this figure, you see this is our original coordinate system x tilde y tilde, and this is northeast southwest. So, in the local coordinate system, they use some kind of an oblique coordinate system. They use this lighthouse and this high peak, and it is given in the problem that lighthouse is 10 degrees south of east. So, 10 degrees south of east. So, we have pointed east here, south of east 10 degrees. Okay. So, maybe that sounds better, and the high peak in some hilly range, there it is 5 degrees north of west. So, perhaps I should give the arrow in this way, north of west. So, that is there. So, and we have the data here in this system, we want to know in our original system, normal system that we use. So, that is a problem here, and there is some given data in the problem that I should have written here. One band that they use 0.2 kilometers, one cos, something they call cos, I will tell you how they do that. So, basically they have this, they do not know 10 degree, 5 degree is not the problem. So, they can always measure along this, or they can always measure along this some distance, and in this coordinate system, this blue coordinate system, they can define any point on the plane, and because they are two different lines, you see these two, in terms of mathematical language, these are two independent vectors, not unit, independent vectors. So, they can describe any point in this plane in the plane of this board. So, the villagers can as well use them, and this is to our normal measurement system, this is given. Okay. So, basically if you look at this from any point here, if you can draw perpendicular, you draw some perpendicular, this is 5 degrees, this is 10 degrees, and we can relate this x tilde and y tilde to x and y. Okay. So, I will write down the equation, because you can straight away find the coordinates from this triangle and say this triangle. Okay. So, if you do that, then it gives something like this, equal to x cos 10 degrees to 1 bands. I will tell you, I do that. So, let us again say this is equation 1, and we write the same way y tilde. So, we are deriving that equation from this figure. So, these two triangles I said using simple trigonometry, y cos 5. These are in degrees, remember, not in radians. So, plus negative, sorry, negative x sine of so this is 2. So, you have now from these two equations you can see that you can easily relate them by a linear transformation of the form of, say, let me write some in capital maybe. So, I can write, say, capital X tilde equal to a x, where x tilde is equal to x tilde and x equal to xy. So, this we have. Okay. So, from that we can straight away write this, the matrix x cos 10 y first one x by 5. Now, before I do that, I should explain this. More than writing the matrix here, that is rather easy part, because the valley systems, they use this coordinate system, as I said, lighthouse, hill peak, high peak coordinate system. In that they used to measure along bands and causes as given in the problem. So, that not only we have these angles, we also need to convert to our system what is that scalar multiple that changes from this unit to that unit. This is exactly that relationships given in the problem actually. So, you can use them and you can write this. Okay. So, you can actually ultimately you will get 1 by 5 cos 10. Remember, these are in degrees, in not in radians, as I said, minus 15 y 1 cos 15 kilometer. So, sine 15 sine 5. Sine 5 degrees is minus 1 by 5 sine 10 minus 1 by 5 sine 10 15 cos 5 degrees. So, that is what you get. So, basically this is x. Okay. So, this transfers to the system that we want, and if you want some data, if you have some data in the normal system and you want to transfer it to the valley system, then what do? You take the inverse of this matrix better be invertible. So, which it is, and to transfer it to valley system you need to invert this matrix, the linear transformation here. So, this is our it. Okay. So, the next part I am not doing, because you just need to invert this matrix where you have to get the other transformation. Okay. So, problem 6 talks about a matrix. We will not do this, we will quickly talk about and go away, because this is actually an easy problem. 2 1 0 2 2 minus 4 minus 1 0 3 minus 1 0 3. So, we have this matrix. What we need to do is the elementary row operation R3. So, third row, I should not give equal to, I should say sign, because it is a row operation, not equality operation. So, R3 plus AR2. So, at some steps, this once after one step of elimination, the R3 should look like this. This row 3 minus 103 plus A times that. So, basically, and also they talk about a column operation that we need to describe, and that says C2 minus A C3. So, why I said I will not do, because this is basically simple. You here you start with an I3 for row operation. For column operation, I should perhaps give a bigger length, because you should start with I4, okay, because elementary matrices you can start with, and then you can on the second row of this I3, second column of I4, you can perform these operations, and if you do and rather verify later on that one is R A and A C, so in this case it has the effect of pre-multiplication, which means multiplying the rows, here it is the columns. So, you will turn out that these operations and these operations are basically equivalent. Okay. So, you will start from I3 for row, for I4, from I4 for columns, and then we will reach these cases. So, this is basically calculation. Question 7 also I will quickly browse through. I will not even write down the matrix. It has got, simply speaking, it has got 4 rows and 5 columns, and we are asked about the rank of the matrix. So, of course, we will do Gaussian elimination, and after Gaussian elimination the number of linearly independent rows or columns, either way, because the rank is always same. So, on that, here we are doing row operations. So, linearly independent rows, then that number will be the rank, and because we know that rank plus nullity equal to columns. So, you can get the nullity also. For the determination for the column space, to determine the column, let's denote CA as the column space of A and the in A as the null space of A. So, if we denote that, then because here the rank will turn out to be 3, okay, that I should give you in advance. First 3 columns will be independent. So, rank is 3, nullity is 2. So, this is 3, this is 2, as I said 5 columns. Now, the column space, they will be basically the linear combination of those 3 independent columns, and for null space, determination of null space, you have to look at those, I mean I will give you, okay, the values, exact values of those transformations. Okay. So, you should get something like this, the final answer, as the row reduced echelon form, as we call it, where all the non-zero entries are below this. So, something like that we will find out. So, the row reduced echelon form for the matrix given in problem 7 is 1 0 0 0. So, you get this 0 1 0 0 0 0 1 0 0.7 minus 0.1 negative 2.1 0 and negative 0.1 negative 0.7 negative 2.7 0. So, something like that. I mean, from this you can see, as I said, the row reduced echelon form goes like this. If I show you this thing here, so you see here, I mean I should give it from here. So that's the form you should get, and from this you can figure out that these are the three independent columns from the structure. And to describe the null space, we just take something like this, 0.7, just the entries. Minus 0.1 minus 0.7 minus 2.7, and the idea is that once you get it, so there are these pivot columns and there are these free variables. In these free variables you are free to choose the values of the variables. So you can as well choose 1 0 0 1. So basically I should say null space is something like this, C1 plus this and C2 plus this. So C1 plus this vector plus C2 plus this vector plus C1 C2 any scalar. So something like that will be the null space. It is not that difficult, just you have to go through the steps of Gaussian elimination. With a bit of patience you will get there. Okay. So number 8 quickly. Number 8 actually is not really different from problem number 1, except for the fact that in this case it is not the symmetric matrix, and that is understood in the form of the decomposition given, in the sense that you will see there it is 1 1 1. Okay, so 1 1 1 is given in one diagonal, which will tell you it is not that, but the rest of the procedure is very similar to question number 1, where you have to just solve those A, B, C, D, E coefficients from the matrix relation. So there is really not much. Okay, so we will jump to 9. Yes, 9 I wanted to tell you because here we are asked to do block operations. In these block operations you have the system of equation. So I will quickly write this. So 2x1 plus 3x3 plus x4 equal to 5, x2 plus x3 plus x4 equal to 2, 5x1 plus 2x2 plus x3 plus x4 is equal to 3, 2x1 minus x2 plus 2x3 plus 2x4 equal to 5, is it? Yes. So this is the system of equations given. You can do that. I mean, you have a 4x4 matrix and you start solving it, but here it has been asked for block operations, and that is what we enforce, because sometimes block operations are very helpful because it can break down the computation to a great deal. So we will rub this off because we will write a few blocks. So that much we note here, that originally the system I wrote here you have to solve at least you have to calculate the inverse of a 4x4 matrix if you want to find the solution of a system. Instead we can write this, we can take these two vectors, these two new vectors, x1 x2 transpose, and we can say y2 is equal to x3 x4 transpose. So basically that way we can divide, this is called block operation, where we can blockwise divide the given quantities in the matrix equation. So from this we can say, if you look at the equations that we gave, we can write the matrix in blocks. So P1 is 2 0, you should get these blocks correctly, otherwise the answer of the problem will be wrong. We will see that here we will end up doing inverse of 2 cross 2 matrices instead of 4 cross 4. Okay. So, P21 5 to 2 minus 1 5 to 2 minus 1 P22 equal to 1 to 1 2. So, you see, as I said that we need 4 cross 4 matrix. So, there would have been 16 entries. Here there are also 16 entries divided in 4 matrices, 4 2 cross 2 matrices. So, we will have these operations that way, and we can now also write the right hand side in this manner. Say Q1 equal to 5 2 and Q2 equal to 3 5. Okay. So, now the whole system that was given has been completely broken down into these blocks, that this vector, this big 4 cross 1 vector has been 1 cross 4 vector has been broken down to 2, the right hand side has been broken down to 2, and the matrix of coefficients has been broken down to 4 4 cross 4 matrices, sorry 4 2 cross 2 matrices. So, with that in mind, if we have this, then we can write, basically we are then solving P11, P12, P21, P22. All the rules of matrices continue to be valid in these operations. So, it is just that we are doing the same thing in a different way to help computations. So, this we solve. So, as the problem has been given here, from this we get this, and from that we get this. So, if we multiply by P11 inverse, that is P11. So, if we multiply by P11 inverse, then we get, basically I should tell you here, here also we are trying to do some sort of Gaussian elimination. Okay. Some sort of Gaussian elimination means, here in normal cases we wanted 0 here, we will want to get 0 here, and we want to get identity here. So, that is why we are doing this. So, we will get this as I2 because we are working with 2 cross 2 matrices. So, it should be that, and P21 P11 inverse, this is P22, yeah, P11 inverse, P12, and this is P21. Okay. So, this will be Y1 Y2 which is equal to P11 So, just like Gaussian elimination, we did this step. Okay. There is nothing very special about it. Instead of numbers, we are working with matrices or the symbol for those matrices. So, continuing like this, if I can now remove this, then we will ultimately get the equation after solving this, and here we have got I2 here, then we have to do one more step for P21 inverse, yeah. So, because here we will get these equations, and then from that the right hand side will come out to be right hand side will be P11 inverse Q1 and Q2 minus P21 P1 inverse P11 inverse. From this, here it will be the matrices after the elimination process. From this we will end up getting this, the matrix as minus 17 by 2, 0, minus 7 by 2, 2 into x3 x4 is equal to minus 27 by 2, 2. So, these equations, this is solvable, x4 equal to 1. From this you can solve x3 x4 and then backward going x2 x1 also. So, that is about 9. 10 I think, just a second. P2 inverse P1. So, this will be. The last problem is basically QR factorization.
Student has come, can we attend that student?
Okay, yeah.
Just ask him. You can directly speak from there,
Yes, yes, Chandrasekhar. Hi. So, number 10 we will not derive, because this is basically you have a matrix A which is given and you have to factorize it in QR, where Q is orthogonal and this R is an upper triangular. R is upper triangular. So, basically this is also rather simple. You have to do the computational steps a bit carefully, because whenever this matrix A is given, from this quickly you can write Q as the columns of Q1, Q2, all of them you can write as the Gram-Schmidt orthogonalized vectors as the columns. Okay. So, that will be U1 by mod 1, I think, is it? Yes. So, we can write it Q is orthogonal. So, Q is orthogonal, R is upper triangular. So, we can write say U1 by mod U1, U2 by mod U2, like this, U2 by mod UN. So, basically you have got Q, that is a orthogonal matrix this way after doing the Gram-Schmidt of the matrix A. So, once you do that, you have got Q and Q are equal to A. So, we can say Q transpose A is basically R. The reason is because Q is orthogonal. So, Q inverse is basically equal to Q transpose. So, Q transpose is I and Q transpose A is R. Now, we have Q transpose, because we have Q from Gram-Schmidt normalization, we have got Q. So, we have Q transpose A was given, we can easily calculate the R, which will give us Q are equal to A, this matrix. So, we will not go to the detail, because Ankur will take you to the assignment 2, which has got some very important problems. So, I think that is that for 1. Ankur, you take over.
Now coming to assignment 2. So, for the first problem, the question asks firstly, after we prove that the inverse of a triangular matrix is also triangular. So, if you proceed step by step, this can be proved by induction. I will just brief you the steps so that you can do it easily. So, let A be a lower triangular matrix. I am taking A to be equal to AJJ will be equal to 0 for all, will not be equal to 0 for all j. Firstly, this should hold true for A to be invertible. Firstly. Secondly, since A is lower triangular, we'll have AJK will be equal to 0 for K greater than J. So we have a lower triangular matrix A. Then we assume A inverse to be B, that we'll take to be BJK. So A into A inverse will be identity, which can be further written as AJL into BLK sigma L going from 1 to N to be delta JK. So for the first element, that is for J equal to 1, we'll have sigma A 1L B L K for L going to 1 to N. This will be equal to A11 B1K, because A12 A13 up to A1N, these all are equal to 0. So from this we get this should be equal to delta 1K. So from this we get that B1K is equal to 0 for K not equal to 1. Now from this whole process we get for the first row, we get that only the first element is non-zero, other than that all are 0. Now after this, now we assume that this whole thing holds true for columns up to say Q, and then if we show that for Q plus 1 this also holds true, then by induction we can say that the inverse of this matrix will also be a lower triangular matrix. So I won't exactly show you the entire thing, you can just try it on by following the similar algorithm as I showed you for the first step. Now by this we can prove that the thing that has been asked, that for a triangular matrix its inverse is also triangular. Now coming on to the next part, now a matrix L has been given and we need to find the inverse of this matrix. So here L has been given to be A, B, D, C, E, F. Now since we proved previously that the inverse of this will also be a triangular matrix, we can assume L inverse to be, we can take L inverse to be A dash, B dash, D dash, C dash, E dash, and F dash. And we'll have L into L inverse to be equal to 1, 1, 1, and all others are zeros. So if you multiply these two matrices, you will very easily you will get A dash to be equal to 1 by A, D dash to be equal to 1 by D, and F dash to be equal to 1 by F. Further, B dash will be equal to minus BA dash by D, C dash will be equal to minus EA dash minus EB dash by F, and E dash will be equal to minus ED dash by F. So if you have solved this case for the L, you can further generalize this whole algorithm for a general n cross n triangular matrix. So I will directly write the result of the result so that you can try it yourself and verify your answers. Now, taking a general L to be L11, L21 up to Ln1, similarly L22 and so, and L inverse can be similarly taken to be L11 dash, L22 dash, L21 dash, and similarly the entire matrix. Now here we have zeros and here we have zeros. So the algorithm will give you the result as L kk dash will be equal to 1 upon L kk. The diagonal entries are simply the reciprocal of the diagonal entries of L, and for the non-diagonal entries, now we have if k is less than n. Now there will be a loop from j equal to k plus 1 to n, and you will get L jk dash to be equal to minus of sigma I is equal to k to j minus 1 L ji p I k upon L jj. So this is the final algorithm. The process, if you follow this process, you will get an inverse of any n cross n triangular matrix. This has been shown for a lower triangular matrix. If we just transpose it, we will get for an upper triangular matrix. So it's just trivial. Now, going to the next question. Okay. Now coming on to the next third question. So in this question, the first part is very easy. Now you have two non-zero column vectors u and v, and we have been asked to find out the rank of uv transpose. So since the rank of u will be equal to 1 because it's a column vector, and similarly rank of v will also be equal to 1 for the same reason. So rank of uv transpose is, as we know, is less than or equal to rank of u into rank of v transpose. So from this, it's very easy to observe that the rank of uv transpose will be equal to 1. So coming on to the next part, here the Sherman-Morrison formula has been given, and now we have been asked to prove this formula and then comment on its utility. So proving this formula, first let me write the formula. A minus u v transpose inverse is equal to A inverse plus A inverse into u 1 minus Vt A inverse u to this whole inverse Vt A inverse. So there are two methods to prove this. Now firstly, you can do by using binomial expansion. We can binomially. Now this term can be binomially expanded, and similarly some algebraic operations will easily give you this result. And there is another method which is easier to this method. You can simply multiply now A minus u v transpose to this whole expression, and this, if this gives you an identity, then this is an inverse of this is proved to be an inverse of this thing. So just you have to multiply these two terms and you will get an identity matrix, and hence you will prove it. So now commenting on its utility. Okay, so now commenting on the utility of this formula. Now, as in numerical implementations, many times you need to calculate an inverse of a matrix, which is quite computationally very costly. And at times you have to then edit the matrix. You have to make certain changes to the matrix. So this formula can be very efficient in doing small changes to a matrix you have already inverted. So this is the main utility, and this is what this formula is often used for. So now coming on to the third problem. The third problem is also an easy problem. I'll just write you the answers and meanwhile brief you how to proceed in solving it. So we have been given that P, which is a scalar actually, is equal to X transpose A into Y. Now we can write this in initial form as Aij Xi Yj. Now for the first part we simply have to differentiate it. We need to find del P by del Xi. Now on simple differentiation you will easily get it to be sigma j is equal to 1 to n A Ij Yj. There is nothing very difficult in this, and similarly you will get del P by del Yi to be equal to sigma j is equal to 1 to m A Ji Xj. So now next we need to calculate the gradient, that is del P by del X. This can be written as del P by del X1, del P by del X2, and so on up till del P by del Xm. So just substituting this formula here, we'll get, now we just need to substitute this formula here for the various values of I, and you will find this to be equal to Ay. Now just solve it, proceed step by step, and you will get this result. Similarly for del P by del Y, now this gradient is similar, and so on, and on solving this result comes out to be A transpose into X. So in the next part, of the question, there has been slight change. We have been given Q to be equal to X transpose AX. Now, as done in the previous part of this problem. Now, if you follow the similar steps, you will get del Q by del Xi to be equal to sigma A Ij plus A Ji Xj, where j goes from 1 to n, and further the gradient value del Q by del X is found out to be A plus A transpose into X. You just have to follow the steps. You will, it should be probably written like capital. Okay, you will just have to follow the steps sequentially, and you will find it very easily. Now coming on to the fourth question. This question is not a big question, but there are quite concepts in this question. So I'll just tell you the concepts involved here. Now, so it's the fourth question. It has been given that A is an invertible matrix. So we can conclude that A into X will not be equal to 0 for non-zero X. Now this is a statement which we will need further to prove it. So we need to prove that A transpose A is always positive definite when A is an invertible matrix. So simply by multiplying X transpose A transpose A into X, this can be changed into AX transpose into AX, which is actually the norm of AX. And now since this is non-zero, this thing will always be greater than 0, and hence X transpose A transpose A into X will always be greater than 0, which gives us that A transpose A is positive definite. Now, coming on to the next part, when A is not invertible, now it's not explicitly given that A is invertible, and we need to prove that A transpose A plus nu square identity is in fact positive definite when A is not compulsorily invertible. So we'll follow similar steps. We'll multiply X transpose and X on the sides, and this will give us AX naught plus nu square into X. Now this quantity is greater than equal to 0, and this quantity is greater than 0 for non-zero X. So we can conclude that in fact this is always greater than 0, and hence this is positive definite. So coming on to the next problem, that is the fifth problem. This is the fifth problem. So we have been given Q matrix and D matrix, and we have to find the solution of X, where Qx is equal to D. I won't write the matrices to save some time. Now we need to find out X as a function of U1 and U2. Now because Q is just a 2 cross 2 matrix, now we can simply invert it to find X, which won't take much time, and I'll just write the result, which we get 1 plus U2 by 2 U1 and 1 minus 1 minus U2 by 2 U1. Okay, so this is the answer for the A part. Now coming on to the B part, this is a bit difficult. So we need to find out the norm and condition number of Q. So we'll take V matrix to be cos theta and sin theta, which gives us norm of V to be equal to 1. This is just we have taken it to keep the solution simple and without losing any generality. So Q into V, now we'll just simply multiply it, and we get cos theta plus sin theta, and cos theta plus minus sin theta into U1. Now this is what we get Q, and then on taking the norm of this Q V norm, now we have to take the norm, and by solving it you can come up to this thing, 2 plus U1 square 2 U1 whole square plus 2 minus U1 square whole square into cos 2 theta minus tan inverse of 2 minus U1 square by 2 U1. Now this is something, and we need to find out the maximum of QV, which gives us the norm of Q. Now, and this is constant, and the maximum of this is equal to 1. Sorry, it's square. So you'll get norm of Q to be square root of 2 plus U1 square plus 2 U1 square and this actually can be simplified to 4 plus U1 to the power 4 square root. Okay, so further we need to find Q inverse norm. Now following the similar steps, now I won't exactly solve it, I'll just write the result which we get. Now we get a similar result, which is 4 plus 4 upon 2 U1. So now we have norm of Q and norm of Q inverse. Now so to find the condition number of Q, KQ, it is equal to norm of Q into norm of Q inverse. Now we just need to multiply these two things, this, and we'll get u2 plus u1 square plus 4 upon 2u1. So we get the condition number of q. Now coming on to the third part of this question, the fourth question, C part. Here we have been given the value of u1 to be 0.01 and u2 to be 0. So we simply put these values and we get the norm of q as 2.000025 and the condition number of q as 200.005. So as you can see, the condition number is quite large. So the matrix is ill conditioned now, and the value of x on these values of u1 and u2 are simply 1 and 1. So now coming on to the D part, where we have to tell how the solution changes on small changes in u1 and u2. So for this we'll differentiate del x by del u1, which will give us u2 by 2 u1 square minus 1 1. And on putting the values of u2 and u1, you simply get here 0 because u2 is equal to 0. Further, when we do del x by del u2, we get 1 upon 2 u1, 1 minus 1, which gives us 51 minus 1 because u1 is equal to 0.01. So as you can see that this matrix is almost insensitive to u2 and quite highly sensitive to u1 at this place. So if we change u2 slightly, there won't be much change in the result of the value of x, but if u2 is changed, there will be a considerable change in the value of x. So we are done with problem 5. Coming on to the sixth problem. Sixth problem I will be skipping because you just have to follow the algorithm of you have to just have to do Tikhonov regularization of this problem. And one thing I would like to tell for the sixth problem is, here for omega is equal to 1, so we will be closing the live session. That will be all for this time. If you have any queries, you can post it and we'll give you a solution, and for the meet you in the next session. Thank you.